Shown in the figure below is AtwoodsMachine. The masses are as labeled in the figure. Approximate the pulley as a solid cylinder. This problem is amenable both to force methods and to energy methods. If we're asked for variables like the tensions or the accelerations, we should go for force methods. If, on the other hand, we're asked for the velocity after a particular distance, we should go for energy methods. The question at hand is to find the velocity of the 6 kilogram mass just before it strikes the floor, and therefore we go with energy methods. The first step in solving an energy problem is to identify all the relevant moments in the problem that we use energy methods to connect. So we identify moment 1 as the moment when the 6 kilogram mass is 4 meters in the air, and we identify moment 2 as the moment just before the 6 kilogram mass strikes the floor. Connecting moment 1 to moment 2 using energy methods requires us to ask ourselves whether we see any work due to non-conservative forces in the process of the motion. Since there's no friction in this problem, we see that there is no work due to non-conservative forces, and therefore we will solve this by the principle of conservation of energy. The conservation of energy equation is realized by setting the total energy at moment 1 equal to the total energy at moment 2. At each of these moments, we'll ask ourselves 4 questions about the energy content of the system. Let's begin with moment 1. At moment 1, do we have translational kinetic energy? The answer is no, because nothing is moving. Rotational kinetic energy, same thing. There is none at moment 1. Gravitational potential energy. As always, that depends upon the location that we call y equals 0. We'll call y equals 0 at the floor, which is the lowest point of the motion for the 6 kilogram mass, and therefore we find that the 6 kilogram mass does indeed have gravitational potential energy at moment 1 of an amount m times g times the y at moment 1, which is 4 meters. Finally, we ask ourselves about springs, and there are no springs in this problem, and so this completes the total energy at moment 1. Answering the same question at moment 2 will require a few more terms. At moment 2, do we have translational kinetic energy? Yes, we do, because the 6 kilogram mass is moving, and also the 2 kilogram mass is moving. At moment 2, do we have rotational kinetic energy? And the answer is yes, because the pulley is turning. At moment 2, do we have gravitational potential energy? This is the term that it is most likely for students to miss in this problem. The answer is yes. Even though the 6 kilogram mass is now at the height y equals 0, when the 6 kilogram mass went down, the 2 kilogram mass went up. And so the 2 kilogram mass is now 4 meters in the air with a gravitational potential energy of mgy. Finally, there are still no springs in the problem, and so this completes the total energy at moment 2. To simplify the expression at moment 2, we'll make substitutions both for the moment of inertia and for the omega 2 term. Since the pulley is to be approximated as a solid cylinder, its moment of inertia is 1/2 its mass times its radius squared. And since the string does not slide while turning the pulley, the linear velocities of both the 2 and 6 kilogram mass are related to the rotational velocity of the 3 kilogram mass via the expression velocity 2 divided by radius. When we plug all of this information in, we'll have the following equation. Notice first that we get a convenient cancellation in that these 2 radii factors cancel with those, after which every term in this equation is either of the form mgy or is of the form 1/2 mv squared. We'll collect all the mgy terms to the left and all the 1/2 mv squared terms to the right, yielding the expression 4g4 is 4.75 v2 squared. We solve this for v2, yielding a velocity of 5.75 meter per second.